$1.25 trillion. That's not a typo. On February 2nd, 2026, Elon Musk just announced the largest technology acquisition in human history. But here's the kicker. SpaceX didn't just buy xAI to get their AI chatbot. They're planning to launch 1 million satellites into orbit, not for communication, not for navigation, for computing. They're building a supercomputer constellation in space that could fundamentally change how our entire civilization processes information. Welcome to Mindcast. I'm Will, and if you think that sounds like science fiction, you're not alone. But today, we're going to dive deep into what might be the most audacious technological pivot of our lifetime. This isn't just about putting computers in space. This is about reimagining the very foundations of where computation happens and what it means for everything from your smartphone apps to national security to the future of human civilization itself. By the end of this episode, you'll understand 3 game-changing insights that most people are completely missing. First, we'll explore why terrestrial computing is hitting a physical wall that space might actually solve. And I'm talking about real, fundamental constraints that even Elon Musk calls unelectrifiability. Second, we'll unpack the seemingly impossible technical challenges of keeping cutting-edge silicon alive in the harsh environment of space and the ingenious solutions that make it work. And third, we'll examine what this means for geopolitics, economics, and quite frankly, the balance of power on our planet. So buckle up, because we're about to explore a story that sounds like it's from a movie, but is happening right above our heads right now. Let's start with a fundamental question. Why space? Why now? The answer lies in what Musk has been warning about for months, something he calls unelectrifiability. Here's what that means in plain English. We are rapidly approaching a point where we can manufacture more AI chips than we can actually turn on, not because we don't know how to build them, but because we're running out of 3 critical resources here on Earth. Land, water, and electricity. Think about it this way. xAI's Colossus supercomputer, the one that just scaled to 200,000 GPUs, consumes enough electricity to power a small city. We're talking about facilities that need gigawatts of power. That's the output of an entire nuclear power plant running 24/7. And that's just one facility. These data centers also require enormous amounts of water for cooling, billions of gallons per year. Plus, you need vast amounts of land in places with reliable power grids and fiber optic connections. But space has none of these constraints. It has unlimited land, unlimited orbital real estate. It has unlimited solar energy. The sun never stops shining in space, and there's no atmosphere to filter out 70% of the energy like here on Earth. And here's the really clever part. It has unlimited cooling capacity. In the vacuum of space, you can dump heat via radiation directly into the cosmic void, which averages just 2.7 degrees above absolute zero. That's negative 270 degrees Celsius of cooling capacity. This is where what I call the Muskonomy becomes absolutely brilliant. The merger creates this incredible closed-loop ecosystem. Tesla designs and manufactures the AI chips using their latest Dojo architecture. xAI trains the models and runs the inference workloads. SpaceX provides the rockets to get everything into orbit and the Starlink network to connect it all together. It's vertical integration on a scale we've never seen before, from silicon fabrication to orbital deployment, all under one roof. To put this in perspective, SpaceX currently has about 9,500 Starlink satellites in orbit. They're proposing to scale that to 1 million satellites. That's more than a 100-fold increase. Each satellite would essentially be a node in a distributed supercomputer floating 340 miles above your head. The combined computing power would dwarf anything that exists on Earth today. Now, I know what you're thinking. This sounds completely insane. How do you keep cutting-edge silicon? We're talking 3 nanometer and 5 nanometer chips, the most advanced processors on the planet, working in the harshest environment imaginable. Space is brutal. You've got radiation that will fry electronics, temperatures that swing from plus 120 degrees Celsius in sunlight to minus 160 degrees in shadow, and no atmosphere for traditional cooling methods.
And then there's what I call the life cycle paradox. Here's the thing. Terrestrial data centers refresh their hardware every 3 to 5 years to keep up with Moore's law and improvements in performance per watt. But traditionally, satellites were designed to last 10 to 15 years because launches were so expensive. How do you reconcile rapid hardware iteration with the logistics of space deployment? How do you keep your orbital supercomputer from becoming obsolete?
SpaceX has actually already solved this problem with Starlink, and it's genius in its simplicity. Instead of building exquisite satellites designed to last decades, they've moved to a high-volume manufacturing approach with satellites that have a designed mission life of just 5 years. When they reach end of life, they use propulsive maneuvers to deorbit and burn up in the atmosphere, making room for the next generation. It's like treating orbital slots as dynamic compute slots that get continuously refreshed. This is enabled by something that sounds like science fiction but is actually happening: Starship's incredible launch cadence. SpaceX is targeting nearly 1 flight per hour. That's not a typo. 1 Starship launch every hour, with each vehicle capable of delivering 200 tons to orbit. At that scale, the economics change completely. You can essentially treat space as an extension of your terrestrial manufacturing pipeline, continuously reseeding the constellation with the latest hardware rolling off the production line.
But what about the radiation? How do you make modern AI chips survive in space? This is where it gets really fascinating. They're not using traditional rad-hard chips. Those are built on ancient, slow process nodes specifically for space applications. Instead, they're using cutting-edge silicon with something called radiation hardening by design. Tesla's roadmap tells the whole story. Their AI-5 and AI-6 chips are designed for terrestrial deployment, but AI-7, also known as Dojo 3, is being built from the ground up for orbital deployment. It incorporates compact radiation-hardened flip-flops, takes advantage of modern FinFET architectures that are naturally more radiation-resistant than older designs, and implements triple modular redundancy at the circuit level. Basically, critical computations happen 3 times simultaneously, and the system uses majority voting to catch and correct radiation-induced errors. It's like having 3 brains solve the same problem and picking the answer 2 of them agree on. And here's where the physics gets really cool. The thermal management problem, how to dissipate heat in a vacuum, is governed by the Stefan-Boltzmann law. The power you can radiate away scales with the 4th power of temperature. So as your radiator gets hotter, the cooling efficiency improves dramatically. SpaceX plans to use massive foldable radiator wings launched on Starship, combined with liquid cooling systems and heat pipes that can handle the extreme temperature gradients. The result? Space cooling is actually about 3 times more efficient than terrestrial cooling.
The memory and storage challenges are equally fascinating. High bandwidth memory, HBM, is essential for modern AI processing, but it's incredibly sensitive to radiation. They're moving to HBM4, which has a doubled interface width that allows for higher bandwidth at lower clock speeds, improving both power efficiency and radiation tolerance. For storage, they're using specialized radiation-tolerant SSDs with end-to-end data protection and firmware that can automatically recover from radiation-induced errors. But here's where this story gets really mind-bending. The Starlink V3 satellites feature terabit-class optical inter-satellite links. Think about what this means. Clusters of satellites can function as unified compute fabrics, sharing data at light speed without the latency penalties of bringing everything back to Earth. You're essentially creating a space-based internet backbone that can process data at the edge in real time above our heads.
Now, let's talk about the broader implications, because this is where things get really interesting from a geopolitical perspective. The U.S. Department of War, yes, they've rebranded from Defense, is already integrating xAI's Grok models into their classified networks through something called GenAI.mil. This gives military personnel access to real-time global insights from the X platform, processed on orbital nodes. Think about what this means strategically.
In a terrestrial conflict, data centers and fiber optic cables are high-value, vulnerable targets. You can bomb a server farm, you can cut an undersea cable, but an orbital compute fabric connected by laser mesh networks that's physically decoupled from traditional theaters of war. It provides a resilient, redundant infrastructure that can process sensor data directly in orbit and transmit only actionable intelligence back to ground units, dramatically reducing bandwidth requirements and sensor-to-shooter latency.
And this creates what military strategists are calling a decisive information advantage. The ability to perform inference at the edge is particularly critical for applications like the military's SHIELD enterprise and direct-to-mobile communications. By processing sensor data from Earth observation satellites, or UAVs, directly in orbit, you can filter out the white noise and transmit only high-value, actionable intelligence. The compute is located at the same logical level as the communication network. The economics are staggering too. Here's a number that will blow your mind. For a 40-megawatt compute cluster, the 10-year operating cost in space is approximately $8.2 million, compared to $167 million on Earth. That's a 20-fold reduction, driven almost entirely by eliminating energy and cooling costs, which account for over 85% of terrestrial data center operating expenses. The grid tax on Earth-based computing is becoming more expensive than the launch tax of putting hardware in space. And here's where it gets even more interesting. As SpaceX prepares for its IPO in late 2026, they're targeting a $1.5 trillion valuation. They're positioning themselves not just as a rocket company or even a satellite company, but as the world's first sovereign off-planet compute monopoly. This infrastructure is poised to become the backbone of both civil and military AI applications. We're talking about computational capabilities that will dwarf everything that exists on Earth today. So, what does this all mean for you? Let me give you 3 concrete takeaways that I think everyone needs to understand. First, we're witnessing the birth of a new class of infrastructure. Just like the internet transformed how we communicate and cloud computing transformed how we store data, orbital computing is going to transform how we process information. The applications we can barely imagine today will be commonplace tomorrow. Think of it as moving from having a powerful computer on your desk to having a million supercomputers floating overhead, available on demand. Second, this completely changes the geopolitics of technology. Whoever controls orbital compute infrastructure will have a decisive information advantage. It's not just about processing power, it's about the ability to monitor, analyze, and respond to global events in real time from a physically secure location that's immune to traditional warfare. We're looking at a new kind of space race, and the stakes couldn't be higher. The nation that dominates orbital computing may well dominate the information age. Third, and this might be the most important point, we're transitioning from a terrestrial civilization to something approaching what scientists call a Kardashev-scale Type 2 civilization, one that harnesses the full power of its star. Musk has talked about this for years, but now we can see the actual technical pathway. Space-based solar collection, space-based computing, space-based manufacturing. It's all starting to connect into a coherent vision of our species' future. We're not just putting computers in space, we're taking the first serious steps toward becoming a spacefaring civilization. The technical challenges are immense. Radiation hardening, thermal management, hardware refresh cycles, launch economics. But SpaceX and xAI seem to have plausible solutions for all of them. The 5-year satellite lifecycle addresses hardware obsolescence. Radiation hardening by design makes cutting-edge silicon space viable. Massive radiator arrays solve thermal dissipation. And Starship's projected launch costs make the whole thing economically feasible. So here's my challenge for you. Start thinking beyond terrestrial constraints. Whether you're an entrepreneur, an investor, a policymaker, or just someone curious about the future, the rules of the game are changing. The next generation of applications, businesses, and even governments will be built on infrastructure that doesn't exist on Earth. The companies that recognize this shift early will have an enormous advantage. What we're witnessing with this SpaceX-xAI merger isn't just a business transaction. It's the first step toward making space the primary location for human computational activity. It's the beginning of a transformation that will make Earth-based data centers look as quaint as the massive room-sized computers of the 1950s. We're living through a pivot point in human technological development, and most people don't even realize it's happening.
That's all for today's episode of Mindcast. If this blew your mind like it did mine, share it with someone who needs to understand what's coming next. Subscribe wherever you get your podcasts, and I'll see you next time when we explore the frontiers of human knowledge and capability. Remember, the future doesn't just happen to us, we build it. And right now, we're building it in space.